All right, guys, welcome to today's lesson on the dilution equation. Starting off with, well, before that, we'll go. Humans begin laughing at 2 to 3 months of age. 6-year-olds laugh at about 300 times per day, while adults laugh from 15 to 100 times per day. You see the digression there. And it's probably, I'm thinking, just because adults have a lot more responsibility, and so everything's not, as carefree as when you were a little person just playing with Legos. These are some scientists, they're doing some crazy calculations, then a miracle occurs. I think you should be a little bit more explicit here in step 2. I think if true scientists are going to be honest with people, are going to realize that they don't have the answer to all of life's questions. They certainly don't have the answer to the origin of life, right? People believe in the Big Bang and all that, and they've got all these kinds of equations that would seem to support that theory, but in reality, if you're honest, we don't know the answer to everything. So anyways, you guys, here's it looks like here that there are 3 separate equations. They're not 3 separate equations. I'm hoping you guys recognize it is actually just one equation. Here's our molarity equation. Molarity is moles per liter. But you guys can see we can rearrange that to deter, based on what it is we're solving for. So we can rearrange this. You guys know if we wanted to solve for moles, multiply both sides by liters, and then you end up with this. If in this I wanted to solve for liters, what I would do is first bring it out of the bottom, so I multiply, and then I divide by molarity, and then you would end up with this. You get the volume in liters and take the moles divided by the molarity. Okay, so let's start with this. Let's say we're starting with a solution. So you guys remember, when we have a solution, when we're storing a solution, we don't just identify the solution. Obviously, we would identify as copper sulfate. You guys remember what a lot of solutions are. So this is actually copper sulfate right here. It's a bluish solution. In fact, it's the copper ions. When you put this in solution, this is salt, it's a metal with a polyatomic ion, separates. The copper plus ions tend to be blue in solution. So just realize, a lot of times people would look at that, if that's a copper sulfate, they would think copper sulfate's a liquid. Copper sulfate's not a liquid, it's a solid, and it's just in an aqueous solution, it's just dissolved in water. So not only do we identify this type of solution, but we indicate the concentration. We'd say it's a 1 molar copper sulfate solution, okay? So let's say we dilute some. Now you guys are familiar with that term dilute, and you guys, this is really big time in chemistry, because if you think about it, in chemistry, what kind of solutions might I, as a chemistry teacher, begin to work with when, let's say, I'm preparing labs for students? Well, you might determine that I would probably start working with concentrated solutions. Right? Because if I have a concentrated solution, what can I always end up doing to a concentrated solution? I can end up diluting it. And you guys should know, by diluting it, what are we doing? We're adding water. So let's say we dilute some, and so we would accomplish that by adding some water. So we have this equation, right? We can kind of figure out. Now, I want you guys to think about in this case, okay? So, oh, you know what? Before we do that, okay, yeah. So let's just say we have a 1 molar copper sulfate solution. We're going to dilute some. And what do? We just add water. Now I want you guys to think about the before and after. We want to look at those situations. So I dilute it, and then you guys notice, okay? So before we did dilution, right? We can kind of set up this molarity equation solving for moles, okay? But here's kind of what I want you guys to think about. What is different now that it's diluted? Compared to what it used to be, what's different? That should be able to see. Obviously the color's different, and you guys could probably guess, why is the color different? Isn't it less concentrated? What else is different? When you guys agree, the volume. So we see the concentration, the molarity is different. We see the volume is different, right? Obviously I had about 20 milliliters, and now I have about 40 milliliters, okay? Volume's different. But then I would ask, what's the same? There's something that's the same between what we had before and what we have now. Hopefully you guys would agree. Isn't it the moles, right? Because there was a certain amount of moles of copper sulfate in the solution, and then what did I do after dilution? I just added water. When you agree, the same amount of copper sulfate, the same moles of copper sulfate is still there. So we can kind of compare. We're saying, let's say we take the molarity, the liters, and the moles. Let's say we have those values before we dilute, and then after dilution. So that's, I'm going to call the ones the values before dilution. I'm going to call the twos the values after dilution. And then after dilution, we have a certain molarity, liters, and moles. Once again, what did we say is the same before dilution and after dilution? Once again, don't we have the same number of same amount of copper sulfate in there? So these are the same, moles 1 and moles 2. Because what we're doing here is we're deriving a certain equation. So then I wanted you guys to think, could I take these two equations and could I kind of combine them in such a way, knowing that mole 1 is equal to mole 2? Well, couldn't we say this? Therefore, if that be the case, couldn't we say this? Molarity of 1, or before dilution, times the volume, or the liter before dilution is equal to the molarity after dilution times the liter after dilution. See what we did? We did this. If this times this equals this, and this times this equals this, and these equal each other, can we say this right here equals that? That's what we did right here. And then, you know what? We're going to just write it, make it a little easier. We'll use a big M for molarity like we do here. Well, a liter is a volume, and technically it doesn't really have to be in liters. We'll see that. And so we'll just abbreviate it as a V. So if I take the molarity before dilution times the volume before dilution, that's going to equal the molarity after dilution times the volume after dilution. This right here, you guys, is the dilution equation, and we're going to use a couple problems to show how you can use that. It says, quick, come outside. What's so important? That's weird. No, where did it go? Dang, there was this awesome snowflake, but now I can't find it. It was right there. So, you guys write this down. It's good to have a problem in your notes. So if we have 10 milliliters of 1 molar copper sulfate, and it's diluted to a volume of 100 milliliters, what is the new concentration? So, that's what we have here. Let's say we have 10 milliliters, right, not much, 1 molar copper sulfate. What are we going to do? We're going to dilute it. So obviously, what are we going to do? We're going to add some water, okay? And we're going to add water until our new solution is 100 milliliters. What is the new concentration? So, you guys, let's just make it real. So we got that. We're going to dilute it. Once again, I'm adding water until I've got 100 milliliters. I want to know what's the new concentration. So, in this case, you guys, at this point now you have two equations that you guys should be familiar with. We have the molarity equation. You guys remember molarity equals moles over liter. Right, that's this one. And now we just introduced a new one, is the dilution equation. So you guys, when you encounter a solution problem, the first thing you guys need to do is determine, okay, which equation am I going to use to get the information I need? So that would be the question I have for you. When you guys read this, which equation would you use? Obviously, you guys would probably realize we're going to use the dilution equation because that's what we're talking about today. But the question is, how would you know that you're going to use the dilution equation here? I think this one's pretty easy because it says it's being diluted. That's an easy one. But there's another way you can tell. If you'll notice, look, we've got 2 volumes. So if you see 2 volumes, that would probably be a good indication we're starting with one kind of solution and then we're diluting and then ending up with a different volume of the diluted solution. So either way, we're going to use the dilution equation. What I highly recommend people do when you're doing this is list what you know. So take the time to list all of these down, M1, V1, M2, V2, okay? What we'd start with is, I would start with your question mark. What are we trying to find? It says, what is the new concentration? What do we want to know? We want to know the concentration after dilution. So which one is that? What's a concentration unit? Molarity, but I want the new one after dilution. That's where my question mark goes. What I would do next is try to put down the 2 values that will go together, okay? Like for example, it seems like right here, 10 milliliters, that volume, goes with this molarity. I have 10 milliliters of a 1 molar solution. So then where would you put that? Well, you'll notice, and you kind of have to just read it. Actually, what I might actually suggest you do next is actually figure out what volume goes with my unknown molarity. And so now it could be a little difficult. So the question is, do I put 10 milliliters or do I put 100 milliliters? Which volume goes with my new concentration? Well, you guys know when you diluted it, you ended up with a larger volume. So even when you read it, doesn't it seem like the 100 milliliters is correlates with my new concentration? That's 100 milliliters. And then what was my initial molarity? It was 1 molar. You guys see I'm just plugging in what I have. And what was my initial volume? It was 10 milliliters. So you guys, at this point, I want you guys to be able to start predicting something about the answer before you do any calculations. So I want you guys to look at this. I want you guys to be able to think, is there anything you can predict about M2 before we punch any calculations? What you guys should predict is, Well, you guys see M2 is my new concentration. What would I expect about my new concentration compared to my old concentration? Well, if I added water, wouldn't you guys agree the concentration would go down? So when I calculate this, shouldn't I expect a molarity that's less than 1 molar? So let's see if that would be true. So now look, I have my equation. Notice I'm solving for M2. So I want to get M2 by itself. So I want to get rid of V2. So I divide, because that's the multiply, so I do the inverse. When I do to one side, I do the other. So that's my equation. M2 is M1 times V1 over V2. So I'm going to put in M1, which is 1 molar, times V1, which is 10 milliliters, all over V2, which is 100 milliliters. And what does that equal? That should equal my M2, my new concentration. Now notice your units, look at units, milliliter on top, milliliter on bottom, they cancel. You guys, that's why a lot of people would ask, Mr. Wilson, does the volume have to be in liters like it did with the molarity equation? It doesn't, because you guys, you'll see whatever units you use will cancel out anyways. So I've got 1 times 10 is 10 divided by 100. You punch in your calculator, you're gonna get 0.1. And what was the unit left? It's molarity, which is what I expected. So what is the concentration of my new solution? It's 0.1 molar. You guys see why this should make sense? What's 0.1? 0.1 means 1/10. You guys, what we're seeing is this is 1/10, and what was the original concentration? 1 molar. We're saying my new concentration is 1/10 as concentrated as the original concentration, and that should not be surprising. Why not? Because what did we do to the volume? Didn't we increase it by a factor of 10? Therefore, the concentration would decrease by a factor of 10. It should make mathematical sense. Okay. You guys are going to finish with one more. Before that, is the soup of the day any good? She says, depends. Well, on what? Hey, Bert, what day did you make the soup? Okay. Last one, guys. Stick with me. How many milliliters of 12 molar hydrochloric acid are needed to prepare 500 milliliters of a 1 molar hydrochloric acid solution? You guys, this is perfect type of problem that a lab tech would have to do. Remember, for a lot of you guys, a lab tech position when you guys go to college make for a great side job, you know, while you're pursuing your education. You guys, in typical fashion, once again, what kind of solutions would a typical chemistry teacher like myself have in the back area in the stock room? They're going to have very concentrated solutions. In fact, here we're talking about HCl, that's hydrochloric acid. It's a strong acid. So this is what I would get from the chemical supply company. I hold it really carefully. This is very concentrated. How concentrated? In this case, sure enough, it is a 12 molar hydrochloric acid. And I don't know if you guys can see it, but it's so concentrated. And so what is it? It's hydrogen chloride, which is normally a gas, but it's dissolved in water, and that's what we get hydrochloric acid. I don't know if you guys can see it. It's almost a lot thicker than your regular just water, because so much hydrogen chloride is dissolved in there. In fact, you guys, I'd be very reluctant to open this up without a base mask, because the fumes are so strong it could like burn your nose hairs. So you guys would imagine I'm not going to have students working with such a concentrated acid. I mean, it could destroy, you know, it's corrosive to bodily tissue. So what do I want to do if I wanted students to work with hydrochloric acid? When you guys agree, we would dilute it down to a lower, more safe concentration. And here would be a typical one. Let's say I want to get it down to a 1 molar concentrated solution, that therefore it's a little safer for students to work with. So what would be the big question? Let's say, so I want to make 500 milliliters for, let's say, a lab, 500 milliliters of a 1 molar hydrochloric acid solution. What do I want to know about this? So I have this 12 molar concentrated hydrochloric acid that I get from my stockroom. When you guys agree, the question at this point I'd have is, how much of this do I need to make 500 milliliters of a 1 molar hydrochloric acid solution? That's what this question is asking. So put that aside, because that's kind of dangerous. So we have our equation. I'm going to just go back to our equation. Once again, when you guys encounter a problem, you guys have to decide, am I going to use the molarity equation or the dilution equation? So once again, obviously we're using the dilution equation because that's what we're talking about today, but how would you know? You guys will see this one's a little bit more difficult. We're using the dilution equation, but notice there's no dilution there. It doesn't say dilute, because you could write it and not put dilute. But what is the hint that would indicate, oh, I got to use this equation, not that one? You guys, a big hint is, you'll notice, look, it's got 2 molarities, indicating we're starting with a certain kind of concentration and we're ending with a different concentration. So if we've got 2 different solutions, that would be the dilution equation. So I'm going to use that once again. what are we going to do, guys? We're going to list what we know. Take the time to do that. People who get lazy and don't go through this step end up putting numbers in spots that it doesn't belong, and they end up with a wrong value. So once again, I say start with the question mark. And what's it asking? It says how many milliliters. So I know my question mark's going to go on a volume because milliliters is a volume. The question is which one. So it says how many milliliters of 12 molar. So you can see my question mark goes with the 12 molar, and you guys should think, well, what's the 12 molar compared to the 1 molar? Wouldn't you guys agree? Before dilution, it's going to be more concentrated, so that molar must be my M1. And if the question is how many milliliters of that, those go together. So I want to know the question mark is the volume of my initial solution, which is 12 molar. See how this question mark goes with this concentration. And then what are we making? We're making, right, and then this information is the second diluted equation. The new concentration is 1 molar, and I want 500 milliliters of it. So, guys, look, we're solving for V1, so I want to get V1. How do I get V1 by itself? I have to get rid of M1. I do the inverse operation. Since it's multiply here, I divide. What I do to one side, I do to the other. M1 cancels. And so V1 is M2 times V2 over M1, okay? So I'm going to put M2, which is, so V1, so right here. M2 is 1 molar times V2, which is 500 milliliters, all over M1, which is 12 molar. Now check it out, guys. Look what units cancel out. Molarity on top, molarity on bottom, cancel. And what's the unit you're left with? Milliliters, which is a volume unit. Oh, before we did this, you guys should have been able to predict something about V1 before we do any calculations. Well, in comparison to V2, I would imagine you guys would realize, doesn't V1 have to be much smaller than V2? Because what are we going to be doing to our original solution? Aren't we adding water, and we're going to end up with a larger volume? So I better get a volume here that's less than 500. And you guys, that's a good way to check yourself to see if you maybe, maybe did entered your numbers incorrectly. You could check yourself if your final value doesn't agree with what you estimated it to be. So 1 times 500 is 500 times 12. Some of you math geniuses might be able to do that in your head. I can't. And I get 42. So now you guys, and you guys see it's milliliters. Now you guys, at this point, I wouldn't just be satisfied if you guys could just get, quote, the right answer, but not really know what you did. Remember, what we're doing here is we're making solutions. So we need to know how do we use this information to actually do something. You remember what we want to do? We want to make 500 milliliters of a 1 molar solution. So I'm hoping that with the little hesitation here, you guys are figuring out, what does this tell me? What am I going to do if I'm making the solution? What does 42 milliliters tell me? Hopefully you guys realize, oh, I figured that is the volume of my initial solution. So what would I do? I very carefully, I have this big old, was it 2.5 liters of highly concentrated hydrochloric acid. How much of this do I need? I just figured it out. This is what these are the calculations lab techs need to be able to do. I need 42 milliliters of this initial solution. So I would carefully pour out 42 milliliters of that solution. And you guys, the rest is really easy. Then what do you just do? Then you just add water. How much water do you add? When you just add water, you'd have a, here, let me, guys, I wanted to get a volumetric flask. Remember, these are what we typically use when we want to get a precise measurement. So I would pour in carefully 42 milliliters with a pipette. You guys will use those when we get into class. You pipette in 42 milliliters of hydrochloric acid. The rest is really easy. Then I'm just going to add water, preferably distilled water. And let's say I use a 500 milliliter, I don't have to do any calculation or anything. I just proceed to add water until it is at the 500 milliliter line on this 500 milliliter volumetric flask. And then what can I say? And now how would I label this? I would label it as 1 molar hydrochloric acid. All right, guys, thanks for sticking with me. Until next time. Bye.